Okay, good morning all. I'm just going to go through some of the electricity stuff with the foundation paper that we're going to be doing in lessons. Now, before we can understand electricity, we have to remember the structure of the atom. The nucleus is the center of mass of the atom. It's where almost all the mass is contained. And we have to remember that it is positively charged because it contains protons and neutrons. Protons have got a positive charge and neutrons have got no charge. So it doesn't matter how many protons and neutrons there are in the nucleus will always be positively charged. The electrons exist in the shells, they are negatively charged. And if we have a neutral atom will have the same number of protons as it has electrons. So if I've got 3 electrons in the shells and I've got 3 protons, then the 3 negative charges balance out the 3 positive charges. Almost all the mass is here inside the nucleus. 99.99999% of that mass is there in the nucleus. And if we wanted to know the number of protons, it is the same as the atomic number. So if I put nitrogen 715 up here, this is the atomic number and this is the mass number. Now, the atomic number is the number of protons. So there are 7 protons in nitrogen because that's what this number says. The mass number is the total number of protons plus neutrons. So if I've got 7 protons and I want to know how many neutrons I have, I just take 7 away from 15 and that gives me the number of neutrons that I have. The number of protons is unique to the element. If I added a proton to this, then instead of having, or if what I'll do is I'll take 1 proton away. Instead of having nitrogen, I would have carbon 615. Now this would be an isotope of carbon because it has 6 protons, that makes carbon. It will have a different number of neutrons. An electric current flows when electrons move through a conductor. So if I was to add a negative potential on one side of this graph and a positive potential on the other side of this graph, so if we were joining our wires together, for example, and here was my positive terminal of my cell and here was my negative terminal of the cell, then this would induce a flow of current. Electricity is a flow of negatively charged electrons. So these electrons will be repelled, they will move through the conductor, and they will go towards the positive. The electrons are free to move because in a conductor they're delocalized, which means even though the electrons are still orbiting around atoms, they have the ability to jump between atoms. They have the ability to move through the conductor. Delocalized electrons just means electrons that are free to move. Now, conventional current is what we use for all of our maths. So we say in our math theory, that electricity moves from positive to negative. The charge goes from positive to negative. Whereas we actually know that electrons flow from negative to positive. These nuclei are not able to move from left to right. They're just not able to move. They're stuck where they are in a solid. They vibrate around a fixed position. Now, the reason why we call it conventional current, and the reason why we talk about conventional current is because before we knew where electrons were, before we were able to discover electrons, we were able to detect, and by we I mean other people who were alive then, we were able to detect the flow of positive things. So we're going to watch this first atom over here. This electron will be attracted towards the positive, and when that electron jumps, it makes this a positive ion. It makes it the overall charge to be positive. So we have a neutral atom here, now it's positive. This electron will be attracted towards the positive, causing a leapfrogging of electrons from right to left. However, the positive charge looks like it's moving from left to right. So conventional current, we say, is positive to negative, and electron flow is negative to positive. Know your circuit symbols, the ones that most commonly come up. Lamps, resistors, variable resistors, voltmeters, ammeters, cells, and batteries. Be on the lookout for this as well. This is a DC power pack, and this is an AC power pack. We're going to be coming and talking about those in a minute. Current is the rate of flow of charge in a circuit, the rate of flow of electrons in a circuit. We can say that the current is the charge divided by the amount of time. How many coulombs per second pass a particular point? The potential difference is the difference in potential between 2 points of the circuit. So if I was to have a bulb and I was to check the potential here, and the potential is the amount of energy per coulomb of charge. Using my voltmeter, I could see that this coulomb of charge here has got a potential difference, a voltage of 6 volts. And then over here, my coulomb of charge has got a voltage of 0 volts. Then this bulb must be taking 6 volts. The potential difference, or the volts, is equal to the amount of energy per coulomb of charge. So if I had a coulomb here and it was carrying 6 joules of energy, that would be the same as 6 volts. Charge is the amount of electricity traveling through a circuit. We say charge is a symbol for Q. That stands for quantity of charge. Resistance is anything that slows down the flow of charge around the circuit. When a negative electron collides with a positive ion in the wire, it causes the positive ion to oscillate or vibrate more. This means that there is a decrease in kinetic energy for my electron and an increase in kinetic energy for the positive nucleus. That increase in kinetic energy causes an increase in thermal energy, which causes an increase in resistance, and so therefore a decrease in current. A series circuit is a circuit with a single loop of wire. We can also say that components are in series when they are connected side by side. A parallel circuit is a circuit with 2 or more loops. If I was to connect 2 bulbs in parallel, then they wouldn't be side by side, but they would be on their own branches of the circuit. Here's a series circuit, here's a parallel circuit. These are connected one after the other, so my electrons that are flowing around the circuit from negative to positive first have to pass through this bulb and then have to pass through this bulb. In a parallel circuit, my electrons will split at the branch. These 2 bulbs here are connected in series. These 2 branches are connected in parallel. And I'll just pause and have a read of the information that's on the screen. We measure current using an ammeter. The reason for that is that ammeters, the reason why we call it that is that the unit of current is an amp. I amp a current. The ammeter is always connected in series with the components so that it can measure the rate of flow of electrons as it passes through. Sorry for these lines, I don't know where they come from. Measuring potential difference or measuring voltage is using a voltmeter. And my voltmeter has to sample the amount of voltage that is coming into the component and the amount of voltage that is coming out of the component. It then tests the difference between the 2 of those to see how much energy per coulomb this component is using. So this would be a 6-volt bulb. It's always connected in parallel, and you can see that there's a loop here. So we call this area here a loop. And remember that the voltage is the amount of energy transferred per coulomb of charge. If this coulomb had 3 joules in it, and this coulomb had 3 joules in it, this would be the same as 3 volts, because it's 3 joules per coulomb of charge. In a series circuit, current stays the same. The current leaving the battery is equal to the current returning to the battery. In a parallel circuit, the current also stays the same, but it does split at a junction. So the amount of current leaving this battery is 6 amps, 6 coulombs per second, but it splits up when it gets to the branch. So down here, I will have 4 coulombs per second, and through here, I will have 2 coulombs per second. Remember that coulombs is just a fancy name for a packet of electrons. The total amount of current in either branch is always equal to the total current in a series circuit, and the total current in a series circuit, in a parallel circuit, pardon me. Total current in a series circuit always stays the same. When charged particles move, they form an electric current. Remember, the charged particles in GCSE is electrons. Electric current is the rate of flow of charge. Now, charge it's a property of a body or an object, and a property just means something that's inbuilt, something that makes it it. So charge is when a thing experiences a force in an electric field. Charge is the name that we give to the fact that when you put some things into an electric field, they experience a force. An electric charge is measured in coulombs. This is a description of electrons. Now, the amount of energy transferred by electrical work is calculated using E is equal to Q times V. So let's say I had 2 coulombs and the voltage that was given from the cell was 10 volts. That means that this coulomb is carrying 10 joules and this coulomb is carrying 10 joules. If I wanted to work out the total amount of electrical work that's able to be done here, then I would just have to add up the amount of energy that there is per coulomb of charge. 10 joules plus 10 joules is equal to 20 joules of electrical work. We can do it an easier way. If we want to find out the amount of energy, we just have to multiply the amount of coulombs we have by the voltage that is coming from that cell, giving me the same answer 20 volts. Here's a question. Give it a go if you want to. Here's the answer. Electric current is the flow of electrical charge, electrons around a circuit. The size of the electric, and when it says usually electrons, is that we usually refer to electrons. The size of electric current is the rate of flow of electrical charge. The rate is the amount of charge per second per unit time. In a series circuit, the current is the same at any point of the loop. So, if I wanted to find the total amount of charge that's moving around the circuit, then I can look at the current and multiply that by the time in seconds. So here's my ammeter, and if it is counting the number of coulombs that are passing by, let's say we've got 2 coulombs in 1 second worth of time, then we say that that is equal to 2 amps. So if this ammeter is able to measure 2 coulombs every 1 second, then we say that that is a current of 2 amps. We say that I is equal to 2 amps because I stands for intensity, well, intensité, because the chap who discovered this was a French person. If I want to know the total amount of charge that has moved around the circuit, then I write down the amount of current, so 2 amps, because I'm saying that it's 2 amps per second, multiplied by the number of seconds that my circuit has been on for. So if it's been on for 4 seconds, then that means I've got 2 amps per second 4 times, meaning that the total amount of current, or pardon me, total amount of charge was 8 coulombs. So remember, Q stands for quantity of charge and I stands for intensity of flow. Here's a question. Now, I'm going to leave these on the screen for 5 seconds. Actually, maybe 6. Maybe a little bit more. And the answer is for the same amount of time. Okay, so quick recap. Current through the component depends on both the resistance of the component and the potential difference across the component. The potential difference refers to the differences between the positive potential and the negative potential. If I have a huge difference between the positive and the negative, then there is going to be more repulsion of electrons and therefore an increase in the amount of current. Resistance is a measure of how difficult it is for those electrons to pass through their components. If there's more resistance, then there's going to be an increase in the amount of collisions between electrons and the positive nuclei. An increase in collisions means a decrease in kinetic energy for my electrons, and if we decrease kinetic energy, then we decrease the rate at which those electrons can flow through the components. So basically, more resistance means less current. The electrical resistance of an electrical conductor is a measure of the difficulty to pass a current through the conductor. The greater the resistance of the component, the smaller the current for a given potential difference across the component. This is something called rheostat. It's a variable resistor. This can change the amount of resistance that it has. If we move the slider up, then it will increase the resistance. If we move the slider down, then it will decrease the resistance. So if you're using a cell of a fixed voltage, 6 volts, then we can use a variable resistor to change the amount of current that's in the circuit. If we put more resistance into my variable resistor, then we'll decrease the current. And if we put less resistance into my variable resistor, we will increase the current. Ask your teacher to show you one of these if you haven't seen them before. Ohm's law, V is equal to I multiplied by R. The total amount of voltage in a circuit is equal to the current in amps multiplied by the amount of resistance in ohms. So if I have 2 amps of current and 2 ohms of resistance, that means I have got 4 volts of potential difference in my circuit. The most common way you're going to see this is to calculate the resistance. R equals V over I. Again, sorry for this funny little line. I don't know where it's coming from, because we've got voltmeters and ammeters are quite common, whereas ohmmeters are not as common. So in labs, in experiments, we tend to calculate the resistance using the voltage divided by the current. Here's what a question might look like. Now remember, all these questions are available in the papers, the higher tier questions I've already done. Now we've already looked at how current and potential difference work in series circuits, and now we're going to also add in resistance. So in a series circuit, there's one loop of wire. For components connected in series, there is the same current through each component. And a nice way to think of this is that if I've got this coulomb, it's negative, and this coulomb, it's negative, and my coulombs aren't able to go around each other. So if this coulomb is being repelled by negative potential difference, then it will bump into that coulomb, which will bump into that coulomb, and they'll all be moving along. Imagine marbles rolling through a piece of pipe. This marble can't get around that marble. This marble can't get around that marble. So whatever rate these marbles are moving, they all have to move at the same speed. Or traffic that's stuck in or a traffic jam. The cars can't go around each other, they just have to follow each other, so everyone ends up going at the same speed. There's the same current through each component in a series circuit. The total potential difference of the power supply, the cell, the source potential difference, is shared between the components. So if this is a 9-volt cell, and if each of these bulbs are identical, each of these bulbs will get 3 volts. If they're not identical, and let's say this bulb gets 8 volts, then each of the other bulbs will get 1 volt. No, that's not true. They will get half a volt, because 1 plus 1 plus 8 equals 10, not 9. The important thing is the total potential difference of the power supply is shared between the components. Now, when we put things in series, when we wire components in series, when we wire components side by side, end to end, in cascade, the total resistance of the components is the sum of the resistance of each component. What does this mean? Well, if this was a 10 ohm lamp, and this was a 10 ohm lamp, and this was a 10 ohm lamp with a resistance of 10 ohms, then the total resistance would be the sum of all those resistances. So the total resistance, our total, would be 30 ohms. This is different in parallel circuits. When we've got more than one loop, then the potential difference across each of the branches is the same. So this is, let's say, a 6-volt cell. This 6-volt cell gives each coulomb 6 joules of energy. But because my coulombs split at these branches, they will still be carrying 6 joules of energy when each of my coulombs enter each branch. So as this coulomb passes over this component, it is able to transfer the total amount of energy that's in that coulomb, meaning this is a 6-volt lamp. This is a 6-volt lamp because this coulomb is coming through this branch, and this coulomb is coming through this branch, so it's another 6-volt cell. So the potential difference across each branch is the same. The total current is the sum of the currents through the separate components on each branch. What does this mean? The total amount of current, or coulombs per second, is split between each of the branches. So if each of these components are identical, then branch 1 gets 6 amps, branch 2 gets 6 amps, branch 3 gets 6 amps. So we can add the total current together. We can add these branches together to get the total current. Now let's say that these aren't identical, these components. The fun thing about parallel circuits is, let's say that this was a 10 ohm resistor, and this was a 10 ohm resistor, and this was a 1 ohm resistor. The total resistance of the circuit would be less than 1 ohm. You don't need to know why. If you'd like to know why, there's a video on that on YouTube, or you can come and ask us for lesson 6. But this is a rule to remember. The total resistance of 2 resistors is less than the resistance of the smallest resistor when we put components into parallel. Now, to measure resistance, we usually measure the voltage using a voltmeter and the current using an ammeter. We can then rearrange Ohm's equation, Ohm's law, V equals I times R, to find the total resistance. The electrical component tested can be changed from the resistor to any other electrical component. What they're saying here is they're referring to the core practical that we did. We tested the changing resistance of a fixed resistor, ohmic conductor, and then we put in a lamp to see any differences. Remember epic rave? The independent variable, what we were changing was the component and the amount of potential difference that we gave to the component that we were looking at. The procedure was to put your fixed resistor in, do a series of different voltages from your power pack, and measure the current and the voltage across that fixed resistor. We would then find the resistance, and that would be our dependent variable. For control, we do the same number of voltages, and we only change in different components. And we repeat and find an average. We do a range, we repeat, we find an average. We do more than one voltage in this cell. We do it more than once, we find a mean or an average, and then we're happy. And then repeat it all for a different component. Okay, electrical energy is spread out or dissipated as thermal energy to the surroundings when an electrical current does work against electrical resistance. What does this mean? It means that when these electrons smash into these positive nuclei, they cause my positive nuclei to oscillate, to vibrate more. This oscillation or vibration increases the amount of thermal energy stored that is in my nucleus, which also increases the temperature. And because this then becomes warmer than its surroundings, my temperature, my heat, is not my temperature, my heat is transferred to the surroundings. All electrical circuits have some resistance, and this is because when electrical energy is passed through a resistor, it does work against it. What I've just described there is the work that's done. The energy transfer is a result of collisions between free-moving electrons and the metal ions in the lattice when a current is applied. Energy transfers in circuits can be reduced by using low resistance wires. If there's less resistance in this circuit, then there is less energy being released. An infrared thermal image is able to show the infrared waves coming off of warm bodies. And when a plug heats up, a plug always heats up when current passes through it. And this can be useful or not useful. Useful heating effects, ovens, kettles, hair dryers, not that I know anything about those, and electric fires. Sometimes we want this to happen. However, we don't want it to happen in our computers, televisions, chargers, and plugs. The amount of energy transferred can be calculated using the equation E is equal to I times V times T. The total amount of energy is equal to the amount of current, so the amount of coulombs per second, multiplied by the amount of energy per coulomb that those coulombs are carrying, multiplied by the amount of time that my circuit has been on for. So if I've got 2 amps, that means I've got 2 coulombs every 1 second. If they have got a voltage of 1 volt, then that means each of those coulombs is carrying 1 joule of energy each. But multiply that by the amount of time that it's been on for, then I can find the total amount of energy transferred. So 2 coulombs, each carrying 1 joule of energy per second, multiplied by 4 means that over 4 seconds of time, I would have 8 joules of energy transferred by my component. Here's an example of what a question looks like. You could look at the booklet videos as well. The amount of energy transferred by an electrical circuit depends upon the time taken. Power is the amount of energy transferred by electrical devices per second. Power is the amount of energy transferred per unit time. So if I'm transferring 2 joules every 1 second, that's the same as saying I have 2 watts of power. Here's an example of what one of those questions might look like. Always remember that we're looking for seconds. Usually we're looking for joules. Okay, so we can also calculate power using voltage, current, and resistance. When electrical appliances are connected into a circuit, energy is transferred to the appliance. The rate at which this energy is transferred to the appliance is the power rating of the appliance. So remember that power is the amount of energy that is transferred every unit of time. You can also find power by multiplying the voltage, which is the amount of joules per coulomb, by the amount of coulombs that there are every 1 second. So if this is 6 volts, that means that each of these coulombs are carrying 6 joules each. And because current is the amount of coulombs per second, then that gives me a measurement for rate. So power is equal to voltage multiplied by current. If I have 6 volts and 2 coulombs every second, then the total amount of power will be 12 watts. P is equal to I squared times R. If we have resistance and we don't have voltage, then we can just put in, I times V. Then we can just put in the equation that we've already seen, Ohm's law for voltage. So if voltage is equal to current times resistance, then I can write, instead of P equals I times V, I can write P is equal to I times R, giving us P equals I squared R. So I've substituted, instead of writing V, I've written the terms that make V. Here's an example of what a question would look like. And another example of what a question would look like. Bear in mind, sometimes they'll give you questions that actually that contain information that you don't need, just so they can mess with your minds. Different types of potential difference. You can have direct voltage, direct current, direct potential difference, or you can have alternating potential difference, alternating currents, or alternating voltage. Direct potential difference just means that I have got my negative and I have got my positive source of potential difference, and my electrons are simply pushed from one to the other. So the electron flow goes from negative to positive. Batteries do this. Batteries do this by having a positive potential and a negative potential, a positive terminal and a negative terminal. So it pushes electrons around in a loop. However, you can also have alternating potential difference. And this is when you have a rotating magnet in a coil of wire or a rotating coil of wire in a magnet. And because it's rotating, then the direction of the electrons change every time. So rather than just going from negative to positive, I have electrons that are being pushed through the wire left and right, forwards and backwards, from one terminal to another terminal changing. So this is a direct voltage. So we'll say it's 2.5 volts of direct voltage. My electrons are simply being pushed. There is no change in voltage. It is a direct current. Because alternating current is made in a rotating copper wire, there will be points where there is zero potential difference in my wire. So my electron starts here with zero potential difference. It is pushed to a maximum. It is pulled back to a maximum. It goes back to zero again. So if I was to do that again, my electron is pushed to a maximum, pulled back to another maximum, and then goes back to where it started. And if I do that while increasing, if I do that without just going over one line, it gets pushed to a maximum, goes back to where it started, back to another maximum, and back to where it started. If we switch that onto its side, that's where we get this image. What do we need to know? In DC current, there is no change in voltage. It doesn't go positive, it doesn't go negative. In alternating voltage, it does go positive and it does go negative. But there is no difference in the amount of energy transferred between plus 300 ohms and negative 300 ohms. Each will give you volts, plus 300 volts and negative 300 volts. It's just about the direction that they're going. So here, my electrons are going positive. Here, my electrons are going negative. Or I can switch it around. It's arbitrary for the sake of GCSEs. And arbitrary means it doesn't matter. So, examples of DC batteries, examples of mains electricity is AC. And remember, AC is 230 volts, because if you licked a plug while it was on, your tooth would hurty. 230 volts. Main supply does change slightly. Wire lights at home might get brighter or dimmer on various occasions, but it's about 230 volts and about 50 hertz. This means that my electrons oscillate, vibrate. My electrons are pushed and pulled 50 times a second. This is fun. Lights dim when a commercial starts on TV during a big show. Lots of people get up to put the kettle on. Okay, most electrical appliances are connected to the mains using a 3-core electrical table, and the 3 cores are the brown, the blue, and the yellow and green. We need to know what each of them do. The live carries alternating potential difference from the supply, usually at 230 volts. So we've got 230 volts here in this little wire. Neutral completes the circuit. So my potential difference, my alternating potential difference, my electrons will flow through this into whatever component I have, and then they'll flow back out through the blue wire. But because this component has had work done to it, then usually of about 230 joules per coulomb, then the amount of voltage in my blue wire is 0 volts. The green wire, yellow-green wire, is a safety wire to stop appliances becoming live. What does that mean? It means that if I have something that's metal, and I have got my 230 joules, it's got a metal casing of some description, I've got my 230 volt wire here, giving 230 joules to my component, and then there are 0 volts of potential difference in the coulombs of charge that are flowing out the other side, then all is well. But if I get a stray wire touching my metal casing, and I then touch that metal casing with my very well drawn hand, God, that's horrendous. I'm going to label this as hand. I'm not even going to be able to write. Oh goodness. Touch this with my hand, then I can have, instead of the 230 volts of potential difference being transferred to my bulb, I'm going to have it transferred to me, which would make me sad. The earth wire is there because it's connected to my metal casing. So instead of this 230 volts going through my hand, instead it will go through the earth wire down to the earth where it's nice and safe. So I'll draw that better. Here is my component. I've got 230 volts coming in, wired up to my component. I have got 0 volts coming out, where it's going to return back into the plug in the wall and complete the circuit for the flow of coulombs. When all is well and good, I've got 230 joules of energy being transferred to my component. The live wire is connected to my metal casing, and it will normally have a 0 volts running through it. But if my live wire was to connect to my earth wire, then there would be 230 volts of potential difference between them. The neutral wire is at or very, very close to 0 volts because all the energy has been transferred to my component. The earth wire itself is at 0 volts because it's only used in an emergency. The earth wire only carries current if there is a fault. If there is a fray in the live wire and it touches the metal casing, then instead of the electricity flowing through the component and giving it 230 joules, my electrons will flow through the metal casing and out the live wire. If I was to touch this and there was no live wire, I would get electrocuted. It can, however, cause a huge amount of current, which will cause an increased amount of thermal energy to be released, which means an increased amount of temperature in my circuit, which could lead to an electrical fire. There's one thing to say. To stop that, we use fuses in my live wires. So if there is a huge amount of current moving through my my live wire, then a fuse will melt. When that fuse melts, then it stops the flow of charge going through my live wire and makes it nice and safe. And here are some questions. And the answers. Woo! And there's the end. Thanks for listening. And now I get to speak awkwardly until I can get this recording because it always surprises me. Right. Hello.